Okay, so hi everyone, this is Sean Mullery from Electronic Engineering at IT Sligo, and in tonight's lecture we're going to be looking at 3D vectors and the transformations on those 3D vectors, the different types of transformations that we can do. So you need to keep in mind the following primary goal. We want to determine things about the real world by looking at images of the real world. So we don't have the real world generally available to us. We only have images which are two-dimensional representations of that real world, and they're two-dimensional projections of the real world. So while its 2D representation is a representation of the world from a specific point of view. So we need to understand the world coordinate system, but we also need to understand the image coordinations or coordinate system and the transformation between the two. Tonight we're mainly going to be looking at the world coordinate system. Okay, so when we get to camera views, we will also need to consider relative movement. So what I mean by relative movement is that if we have an image of an object and we rotate the camera in a clockwise direction, what will happen is that the result is that the image of the object will appear to be rotating in an anti-clockwise direction. So you need to be aware of that which is moving and what is the effect going to be, so that you make sure you kind of keep all those things straight. If we wish to describe a position of a point in the world, we will need 3D coordinates. So we'll have X, Y, and Z, okay, for the three dimensions. We put the little transpose there just to say that it's going to be a column vector is how we would normally describe it. So to describe how a 3D point would change under 3D transformations, we'll once again use the homogeneous coordinates, changing the 3D coordinate to X, Y, Z, comma 1. And I did promise it'll be, I think, next week that we will formally explain why it is that we're using homogeneous coordinates and what the effect of those are. But for the moment, you'll just again just take it on faith that we're going using that, and you can just assume for the moment that value is always 1 until we say otherwise. Okay. So we're really just going to go through something very similar to what we did in the previous lecture on 2D geometric transformations, which is we're going to look at what are the matrices going to be for the different types of transformation that we can do on 3D vectors. So translation, first of all, the matrix for this is just, you have the identity down there. So we have the identity down there, and we have the three movements that we can make in the X and the Y and the Z direction. Does anybody want to take a guess at how many degrees of freedom we have in this situation for a 3D translation? Yeah, don't see anyone else typing, so I'll take Maurice's answer. It is indeed 3. So the 3 are the TX, the TY, and the TZ. Everything else stays the same. Okay. So I think Colin said 4. So hopefully you can see that there's only 3 there. There's only 3 values that can change. Everything else is just a constant value. Okay. And of course we have our different ways that we can lay this out. So you will see in different different pieces of literature that they will sometimes put these as blocks. So they'll put the I there just by the fact that the I is a full block of a 3 by 3. The 3 again, the T again is a 3 vector there, and then we've the 0 transposed, so it's 3 across the way there, and then we have just a value of 1 there. So you can see how they can build this up, or they can show it as a 3 by 4 matrix either if they're not showing the homogeneous coordinates. Okay. Don't think we need to keep all those highlighters. So the next one is the rigid body movements, which, if you recall, I said to you before, they can contain rotations and translations. So we can move in 3D, but we can't change the scale. We can't change the angles in between things. So we can't change lengths and so on. And remember, we're just in the 3D world at the moment. We're not in a camera view of that. So if we just move things about in the 3D world, they don't change. Now, I'm aware of the fact, obviously, that you're watching this through a camera. But for me, if you imagine the situation where you're here with me in the 3D world, this is moving about in that 3D world. Angles don't change, lengths don't change, and so on. And because of that, also volumes don't change. And in one of the later short lectures tonight, we'll be showing some of the mathematical formality behind that. But again, it's really the intuition you need more than maybe the mathematical formality. So, or in this case, we can split this up into this section here, which is a 3 by 3 matrix, which has 9 different values related to the rotation, and we see tx, ty, and a mistake. Have I that mistake everywhere? No, thank you. That should be tz. Okay, so that's a z value. I'll maybe make that a bit smaller. So that should that there should be tz. There, just be careful of that. Okay. Sorry, no, hang on. Why is the notation 1122? You're just talking about positioning, is it? Is that what you're asking me? That's just its position within the matrix. Are you familiar with that? Yeah. Yeah, exactly. Yeah. So you have come across this before. Yeah. So it's just to tell each of the different ones apart is all. It's just an indexing. Yeah, that's okay. Make sure to stop me in any stage, because there may be many things that I assume that you know, and if you don't, and it's going to cause you to miss something, just stop me like that. That's perfectly fine. I might ask you for clarification as to what you mean, but that's perfectly okay. So we can see that there are 9 of those, and then we have tx, ty, and tz. And we split those up there and there. How many degrees of freedom would you be seeing here, do you think? Yeah, okay, you're saying 4 values can change. Okay, so I just want to see what Liam's writing here. Yeah, is anyone else having the same problem Liam's having? It's possibly just on your own end there, Liam. Okay, so Liam, look, if it does, you can pick things up in the recording anyway. Okay, so just to be clear, on face value, there are actually 12 values here that could change. Okay, we've 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each of those values are different. The fact you have OR11 and OR12, that means that they are different indexes and they could be different. But it turns out that in terms of a rotation, a 3D rotation, we can only we can perfectly well describe it with just 3 rotations, which are the rotations around the x, the rotation around the y, and the rotation around the z. So that's only 3 degrees of freedom. So as it happens, and this is an awkward one, this actually would have 6 degrees of freedom. Okay, but it's not obvious from the numbers there, and while those numbers might all be different, if they are a proper rotation matrix, which obey all the rules that I'm about to mention here, that means that they are in some way dependent on each other and all dependent back on just the 3 degrees of freedom related to the rotations. Okay, so it would have 6 degrees of freedom. Now, so OR is a rotation matrix and is an orthogonal or orthonormal matrix. In other words, if I multiply it by its transpose, I will get the identity matrix. No, we're not counting. So Vin is asking, are we counting 3 rows of OR as well? We're not counting the 3 rows. All I'm telling you is that these pieces of information here. So we are sorry, as in we're counting things that are in those 3 rows. Yes. Okay, because of course they can change. But what I'm saying to you is that there will only be they will be the result of 3 different degrees of freedom that can cause those 9 numbers. Okay, so they're all related to each other. So this section in here, just that 3 by 3 Okay, so that section, that 3 by 3 there is, I'm actually sorry, I haven't fully understood plus TS. I'm not sure what you mean. Oh yeah, plus the T's. Yes, is correct. So altogether there would be 12 of them there that we're looking at. Yeah. Okay, so going back to the rotation matrix here, which is the 3 by 3 part of it, what we have is certain rules with regard to that matrix, which is that it's orthonormal or orthogonal. So that means that if I multiply it by its transpose, I will get the identity, which means that if I take my rotation matrix, or transpose is equal to the inverse of or. Okay, those two things are the same. And that comes up again and again, where we're able to do this multiplying it by its transpose later on, which is the same as multiplying by its inverse, and that's a helpful one. It doesn't happen for all matrices, obviously, but it does happen for orthogonal matrices, as I said. Okay. The other thing about a rotation matrix is that it must have a determinant of +1. Okay. Now, strictly speaking, if it had a determinant of -1, that would be a mirroring rather than a rotation. Okay, so that would mean that everything was mirrored back on itself, which is not necessarily that's not permitted within a rigid body motion. There's nothing I can do to this object in my hand in order to do a mirroring on it. So note that we haven't parameterized this yet. That's because it's much more difficult than in the two-dimensional case to actually come up with the parameters. If you remember in the 2D case, we had a cosine and a sine of theta, and we were able to do that and actually determine what the angle would be. So we only had 1 degree of freedom in that case. We've 3 here. This is much more difficult. So here we require 3 angles, 1 for each axis. So we leave that parameterization for the next section of this lecture. So similarity then. As you can see here, what we have, we've the same as what we had previously, which is the 6 degrees of freedom. Okay, 6 degrees of freedom, which is that we have three translations, 3 by t's. Okay, we had the 3 rotations, so the 3 angles of rotation. Now, we also have a value s here, and you'll notice that value s is the same in each case. Okay, if you're a little bit concerned about the way it's written there, it's simply just that the s is multiplied by each of these different 9 values. Okay, but it's the same value of s is multiplied by it in each case. Now, clearly, we said that the determinant of that rotation matrix is just 1, but if I multiply it by s, then that is going to multiply up the size of the determinant. So what this does here is that we can rotate, we can translate, but we can also make things bigger. But if we make things bigger, we have to make it bigger the same in every direction. This is why it's called similar, because we won't change angles and things like that, but all our lengths will all go up by a value of s, and that's what this means here. So this will have 1 further degree of freedom here, which is the value of s. So we'd have 7 degrees of freedom here altogether. Okay, not our 6. So just for later on, I'll remove that in case that causes confusion. So they are the 7 degrees of freedom that we would have for this, and you can see how we would lay this out. Now, we mentioned affine before, and we said that that really the affine allows us to do rotation, translation, similarity, but it actually allows us to change the individual lengths. Now, the only thing it doesn't allow us to do is to change parallelism. Okay, so if we have lines that are parallel, they will stay parallel. And you can see here that this properly now has all of these individual degrees of freedom, as well as these 3. So this is going to have your full 12 degrees of freedom in how these ones move. Okay. So that's fine, and that's the affine one, and therefore we would have to come up with numbers for each of these as to how this would work. Now, once again, affine could be split down into the different things. In other words, we could split it down, or we could try to split it down into particularly that A there. We could try to split that down into its rotation and the different values of s. So in other words, s1, s2, or maybe s11, s12, and so on. Split them down into the different directions in which they're scaled. But as I said, that's going to be quite difficult because you've got a 3 by 3 matrix and you have to try and separate out the part that's an orthogonal matrix that is a determinant of +1 from the part where all the different numbers are changing. So that's much more difficult than it was in the two-dimensional case where you only had the one angle of rotation that could occur. Okay, so that's the affine matrix. You can see how these are very, very similar to the two-dimensional cases that we looked at previously. Okay, the final one is the projective matrix, and you can see here that any and all of these values can change. I did mention to you in the last day that we have a scale problem associated with projective matrices, which is that there's an ambiguity there. And what we would normally do is we would normally set this value to 1, and from that you make all the other things stay in line with that. You could then change it to any other value and everything else has to go up by the same amount. Okay, so we would often think of this as, rather than necessarily 12 degrees of or 16 degrees of freedom, maybe only 15 or so. Okay, and there are other issues regarding it as well. Okay, so projective is very important to us because it relates the 3D coordinates to a point of view, otherwise known as the center of projection, i.e. where the camera was positioned when it took an image. We'll be discussing this a lot throughout the module. Okay, so we'll be looking at these things a good bit more in what we do. So with regard to this, it is just important to realize that it's, at some point later on, what you're going to be trying to do is you're going to be trying to say from the images that we have, what sort of things happened in order for us to get from one image to the next. And remember that if you're looking at images of the world, it will be a projective transformation, and therefore you will have all 12 of these possible numbers. And from that, it's a matter of trying to figure out, can we constrain things in some way in order to try and figure out maybe the 3D motion that has occurred, such as the rotation and the translation, or how far are things from the camera, so that we can actually work our way back to that in that way. Okay, so that's a matrix we'll be coming back to at a later stage. So I mentioned that I was going to talk about these 3D rotations and the issues surrounding them, and as it happens, they're quite problematic. Okay, so unlike the 2D case, which is relatively straightforward, the 3D rotations are not, and it's because of the 3 angles that are involved. If we take a 3 by 3 rotation matrix, or we have 9 unknowns arising from the 3 degrees of freedom. So that's just going back to what we had there previously, which was this one here. The OR11, OR12, OR13, and so on, they are the 9 things that are unknown, but they're formed from just 3 degrees of freedom, and they also have to, have I still got it there? They also have to obey all these rules that we mentioned down here. Okay, so this sort of thing here, they had to obey all of those in order for it to fit. Where are we there? 3D rotations. So if we take if we try to determine these unknowns by the usual methods, such as least squares or something like that. So let's say you've got 9 unknowns and you manage to get 9 equations that will be able to help you to constrain those and try and get them down. Well, we'll get a result, certainly. We can find a best fit. The problem is that best fit, how do we know that best fit is an orthogonal matrix? Okay, it's very difficult to try and optimize using least squares or any of those other methods. It's very difficult to optimize it so that you also get the situation that your 9 values turn out to be an orthogonal matrix, and that they have a determinant of 1, and that the transpose is the same as the inverse, and so on. That's very, very difficult to try and do. It's not really possible to do. So this is one of the problems that we have, because the situation we're going to end up in is that we're going to have the problem of trying to find out what those values are, and then trying to figure out what rotations did the camera undergo in order to get from where it was to where it is now, or between 2 camera views that we have. Okay, so you can see the sort of problems that are beginning to rise there, and how we're going to maybe try and solve them. So we can certainly find a result for the 9 unknowns, but how do we ensure that the resulting OR is an orthogonal matrix and has a determinant of +1? That's much more difficult. So If we just decide on rotations ourselves, in other words, if we're working in the forward direction, let's say we're not trying to work our way back, we're working in the forward direction. I want to tell a camera to undergo certain rotations or whatever. That's fairly easy, and we can separate it out into the rotations around the three axes separately. In other words, rotate around the X, then rotate around the Y, then rotate around the Z in order to get to wherever I want to go. And I've given you the three matrices there. As you can see, the RX, the rotation for X and the rotation for Z are both quite similar in that all we really do is we move the information down the way there, so that this moves back up the way for this one. It just moves into a different position. The Y is a little bit more complex because you can see that the two signs have switched. Okay, so the negative sign on the sign of the angle has just swapped around. It's in a different position. Okay, and it's spread out to where it is. So that's a bit more difficult of one to remember. Okay. So alpha, beta, and gamma are called the Euler angles. So if you ever come across this idea, the Euler angles, this is what they are. To get any combination of rotations, what we do is we multiply it by one matrix, then by the next, then by the next. So remember, what we will have is we'll have a 3D vector, like so. So we'll just call it, let's say it's X, Y, and Z of some description. Okay. We're ignoring the homogeneous coordinates here for a second, although we could deal with that too by just putting ones on the end. What you would do is you would multiply that X, Y, and Z by this one here first of all, and then the results that you get, because again you'll end up with a 3 vector, you'd then multiply by one of the other ones in order to decide where you're going next. Okay, so that's all you'd have to do, but it has problems. What order do you do it in? Do you do X first, then Y, then Z, or what way do you do it? And it turns out that, let's say I want to rotate only around the X and the Y and not the Z. If I rotate around X first and then rotate around Y, or if I rotate around Y first and then rotate around X, by the exact same angles, I end up in a different place. So that's a serious problem, because it turns out that the order of these things matter, and therefore we really need to find a better way of deciding which way our rotations are going to go. Okay, so this is a problem that we're going to have to try and solve. There are some other issues to do with rotation. We're going to find most of the 3 lectures tonight have things to do with rotations. So moving through the parameter space of alpha, beta, and gamma is not always smooth. There are strict mathematical definitions for smoothness, which I'm not going to go into. But what this really means in practice is that if you make a small change in the overall movement, that does not necessarily mean that you're going to have a small change in each of the alpha, beta, and gamma. Okay, so a tiny change can often lead to one of these having a sudden spike in value and having a much larger value very, very suddenly. So sometimes a small change will require a very large change in one of the Euler angles in order to actually achieve that. Now, this has different names depending on what you're in. So in robotics, where each rotation is very visible, you see a robot and it's moving, this is sometimes referred to as gimbal lock, because what happens is you want to make a tiny movement from one place to another, but it turns out that in order to do that, you've got to come swinging back in some way and try and get back into some position in order to do that. Okay, so in camera views, it's not as big of an issue as it would be for something like a robot. But do remember that if you're trying to move a car that the camera is attached to, and you're trying to make those decisions based on that, you have effectively got a robot, and you have problems with rotation because you've got just the steering angle of the car to work with, and clearly there are certain angles that if you've got to the full lock of the steering, okay, where are you going to go from there? What are you going to do? So you can see how these issues would come up in the autonomous driving example as well. You're very constrained by how the car can actually move and so on. And if you add those constraints into all of these, you can see you have a considerable bunch of problems to deal with. Okay, so that's one of the issues. That parameter space not being nice and smooth means that we can't make infinitesimal changes that actually move us along it and move us from one camera position to another. It doesn't work as easily as that, and we have to find ways around that. So this is not to suggest that the Euler angles are of no use at all. It's just that you've got to be aware of all the problems that surround them. So in particular, where simple known rotations are required. So let's say, for example, you have two fixed cameras and you know the angle in between them. And in many cases, two fixed cameras, they don't move in any way on the Z and they don't move in any way on the X. They might only move on the Y or something like that. In those cases, the Euler angles can be very useful for you figuring out where one thing will be in one view and one thing will be in the other view. So if you have a lot of other information, and particularly in the situation where you're dealing with the rotations between the cameras are static, they're not moving. Once you have them figured out, you can have a very simple translation between them and a rotation between them, and that's perfectly fine. And the Euler angles would be very useful in those cases. However, in the general case, it would be we'd like a better method. Without getting too deep into the mathematics of vector spaces, the space of rotation matrices is not linear under addition. Now, I will mention this not in the next short lecture, but the one after that. I will mention about this space that of rotation matrices that if you add two of these together, you don't get another rotation matrix. Whereas if you multiply two rotation matrices by each other, you do get a rotation matrix. And this is the problem that we have to try and solve, because we really prefer, when it comes to making very tiny changes, and we need to make tiny changes if we want to determine the entire path that a camera has undergone in between two movements. To do that, we really need to be able to add on little bits. And the problem is that when you add something to a rotation matrix, you don't get another rotation matrix, or you're not guaranteed to get another one. So we have to try and work our way around that. So a common solution to this is to change to another space which is linear, and move about in that space and then come back again, then do your mapping back to it. And we'll in before the end of this evening we'll get to that. We'd also like to determine a smooth path between two views. So just to be able to see that kind of smooth path that we can get between two places as to how we do it, rather than just determining the full rotation between two views that we might get, we might want to say, well, what are each of the individual little paths that we took, each of the individual rotations and translations that we took in order to get from one place to another. So for example, the path that the camera took to get from one position or orientation to another is particularly useful when the views all come from one camera, which only takes an image at some sample period, and we may wish to interpolate between these two. So if you can imagine, if you've a camera on a car and you're moving and you want to determine the path along which that camera has taken, so that you can tell something about your location and what path you're moving through and so on. From that point of view, it's obviously very useful to have each of the different positions. You don't expect that between views the camera was just, or the whole car was just picked up and planted somewhere else. And that's not going to happen. Okay, so I'm going to end that recording at that stage there, guys, and you can take a 5-minute break just while I upload this, and we'll come back and we'll do a second lecture at that point.